from Berkeley, now he works also on many other subjects. He's a fellow of the IEEE. Before he went to Berkeley, he was with the University of Illinois at Urbana, and then before that he was with AT&T Laboratories. He has received two Berkeley awards from the IEEE Single Research Society. Most of us have one, he received two. And he also has received an Excellence in Junior Faculty Award at UIUC, which is called by the name of Frank McMaster Scholar Award. And he also has received the Ocasio Prize for Excellence of Research in Berkeley. Today he will talk to us about smart networks of dumb sensor nodes used to distribute the signal processing and coding. I know many of you are interested in this subject, so welcome. Thank you for coming.
Thank you very much, John, and thanks for the honor of this colloquial invitation. I actually haven't been to Maryland campus in a long, long time, so it's very great to see old friends also here. Yeah, so the title is more meant to be a provocative thing than really that much substance. But at the same time, I do want to kind of follow the spirit of the title. It was just meant to make you come to the talk. Now you can. So I do want to acknowledge that most of, not all of the work is done by others. I'm just here to recite what they've done. And these are all my collaborators from current and past. Some of them have moved on and others are still around. So I'll mention their names as we go. Okay, so since this is a sort of colloquium talk, I figured I should start with some high-level slides. And sure enough, nothing higher level than the dean of UC Berkeley, Richard Newton. I guess when you become dean, you make plots like these, so I stole this plot from him. Essentially, it's to put in perspective that if you look at the history of computing and you plot the size of computers as measured by the ratio of people per computer on the log scale. So on the log scale, it's supposedly linear. So we start from mainframes to mini computers, workstations, PCs, laptops. So now we have reached the era of sensors, because that's what nature ordains, that we have to work on very small things. And you also see that the functionality of these computers is changing vastly from purely number crunching and data storage to something more interactive and productive and portable to something much more physical. You're streaming information to and from the physical world. So it's no longer just the internet crowd. You need physicists, you need control theorists, you need everybody in the mix here to sort of make the system work. So also historically you see that sensing has led to a much better understanding of the world, whether it's telescopes or microscopes. So this is supposedly the world's first microscope. It's a piece of art by itself. It looks beautiful. So these inventions have certainly been extremely influential in our understanding of the world. So now we are in the era of these kinds of sensors. There's the Berkeley Smart Dust, Intel modes. Everybody is getting in on this act now. Where are we headed? So what are we doing with these sensors? So first generation sensor net applications, this is kind of my take on this, is that we put things to fairly practical use. System building of sensor networks is rampant. Berkeley has a lot of action in that. I'm not really affiliated with any of them other than just finding out what they're doing and just getting inspired. But Deborah Eston is running a big center in UCLA called the SENSE NSF Center. And David Culler, my colleague in computer science, has built a couple of systems based on the Intel modes and the Berkeley modes. And there are projects going on relating to monitoring environments, monitoring structures, and even interacting environments. So anybody know what this is? That's the Golden Gate Bridge. So they put sensors on the Golden Gate Bridge to try to sort of find out fine-grained structural information about how it reacts to things like traffic, tidal, air pressure, wind, so they want to monitor this in a very, very close way. There are projects relating to finding out the sort of nesting habits of, I think it's called the petrel chicks or something like that, off the coast of Maine. So again, students get to go to the coast of Maine and play around with sensors there. So if nothing else, it's a lot of fun. There's also a lot of interest in doing smart buildings, so you can have very fine microclimate control. So you don't have, the thermostat being heated by a monitor and making, affecting the entire room temperature based on that reading. So all these things are going on, and here are some web pages if you're interested in more detail. But for the most part, I would classify these applications as sort of small sensor networks, few nodes, and get it to work is the main point. And they kind of have more of a stovepipe architecture where you build off-the-shelf products and then make some protocols and let's get things to work. That's been more or less the philosophy. Now, I'm kind of grossly exaggerating a bit, but so that as we look ahead, peeking into the future, so if I want to put on my science fiction hat, what are some of the more sort of forward-looking or wild-thinking applications? One thing that's being considered is putting these at very, very high density, for example, on the wings of an airplane. To measure, for example, it's called an airplane skin. So this would be giving you very, very fine-grained information about things like cracks developing, or even to improve the dynamics, the wind dynamics, or even just if you have a crack, how you can kind of rebuild your wings on the fly. So all these things need very, very high spatial density. So you need large density nodes. Likewise, smart surfaces where you would potentially have, sort of touch-oriented things and things reacting to feel and words and so on. Communications backplane. This is an interesting one. I'll talk a little bit about this in more depth, more technical depth. But essentially, the vision might be one of Intel actually has a project called paintable computing, where you mix the sensors inside paint and you paint the wall with it. And that forms a computing infrastructure or even a communications infrastructure. And the goal will be how much data can you actually send reliably. So it will be a wireless medium. In addition to having 802.11 and other things, you can have your wall actually send you information. Smart walls is what they say. And of course, the ultimate is injecting it into your bloodstream. This is probably a little far out, but these are supposed to be red blood cells, and this is your sensor. Okay, anyway, so
maybe smart too, right?
Yeah. So anyway, so question is, can we get there? If you're going to get there, how are we going to get there? So my sort of thesis on this is mainly that you have to think of scale, not think of scale after the fact, think of scale up front. And likewise, things like robustness, which is one of the main reasons why these small sensor networks that they build today stop working when you add them to a few hundreds, is because they're not taking care of the robustness issues. So I think you have to think scale and robustness up front. And that way, the easiest is to think about small, dumb, and dense. So dense can be taken both ways, right? Now, in this context, let's consider two species that have been extremely successful, or humans and ants. The humans, of course, are characterized by brilliant mind, brilliant brains, if you will. But let's kind of look at some statistics, some very telling statistics. Turns out that humans occupy 10 to 15% of all terrestrial animal biomass. That means the weight of all human animals on Earth, 10 to 15% of them are occupied by humans. That's a sign of success, right? Because, well, it could have been higher, but that's the number. You have 10 to the 9 neurons per node, so that's your brain. That's supposed to be a big, you're supposed to indicate you're a very complex, smart creature. We've been around for about 100,000 years. Let's look at ants. Amazingly, they also occupy the same biomass. Obviously, there are lots more of them, but percentage-wise, they are equal to us. They are not as smart. 10 to the 4th times less smart. 10 to the 5th neurons per node. But they've been around for a lot longer. In fact, 1,000 to 1 ratio of how many years they've been. So these come from this book, which is, I think, makes for interesting reading. So that's kind of what the two worlds are. The humans are extremely complex creatures. The brain is very, very difficult to figure out. And I think people have been trying, but it's been a very tough task. I claim it's much easier to create ants than animals. So I follow the philosophy that let me first try to understand how these ants work. And I am not the only one. I think John and others have done very interesting projects related to that. And this is more of a motivational tool. I'm not really working with ants or really being inspired by ants. There are others in my department, like Ron Fearing, who are actually working with, inspired by the way insects fly and things like that, real robotics. Okay, back to Earth, right? So that was supposed to give you an overview of kind of where the philosophy of some of the things we're looking at comes from. Now we'll get more down to earth, and we'll kind of give 3 explicit examples. They'll be more like excerpts, especially starting from very little here to more and more. 3 projects relating to signal processing and coding. I'll talk about sampling, high precision sampling, decentralized storage, and then something that relates to the smart walls idea of doing reliability with very, very cheap but lots of untuned radios. And then, time permitting, I'll go into video, which is another sensing medium, and I'll sort of talk about how you should follow the sort of the dumb or the complexity story there also in architecting new ways of thinking of video. Okay, so this is supposed to be a very brief overview, so I'm not going to talk any details about this. So the point here is to see, of course, when you're throwing sensors on the field, every signal processing person will tell you you're sampling. And of course, sampling is the oldest thing in signal processing, so that's the first thing you should address. And so let's first think of a very simple case, a band-limited, one-dimensional field. And this is supposed to be a spatial temporal field. So let's do one dimension in space, and then you have the other time dimension is always there. So we want to talk about spatial density. That's kind of what motivates a lot of the work. And we want to understand things like, first, understand the constraints involved. We all know that sensors are small things. They're supposed to be dumb things. So limited in computation, power, and therefore reliability, because they'll be sleeping half the time, or more than half.
I mean, this is a little bit arbitrary assumption that they have to be dumb. I mean, we have smart sensors, and because of the economy of scale,
Yes.
it's not going to be much more expensive. I mean,
Yes.
why they have to be limited?
No, individually.
Yeah, individual.
Yeah,
Each individual. Why couldn't it have some significant intelligence? You can have embedded processors that are...
Oh, no, you can. It's a matter of cost. It's a matter of how much. So I'll get to that. So that it's a matter of, if you want to make it really, really cheap, then you have to scale down what individual things can do. And also, if you want to power them, you want to scavenge energy from the environment and things like that.
That's a principle that's been proven limited, if not wrong, with many other things in the past. I mean, when cell phones came around, people said they were going to be very expensive to do things like the features they have today. So it's an economy of scale. If you have a lot of them, then you'll be very intelligent on the chip.
I agree with the economies of, in terms of these things will get more and more intelligent as they get bigger and more deployed. I totally agree with you. But I don't think I disagree with your basic premise. I'm exaggerating the dumbness part. What I'm more interested in is what do collections of them do, more than individual. That's kind of what I mean. Okay, so the things that we can ask here are trade-offs between precision and density. So by precision we mean how many bits do you want to put into these sensing devices. So if you want a 8-bit A to D, that's going to suck a lot of power and cost more than a 1-bit A to D. On the other hand, you can have more of them. So likewise, trade-offs between the density and, suppose I want to reconstruct the field to certain accuracy using whatever norm you want. Let's call that D. So how does N trade off with D? And can you furthermore do this in a distributed way to make sure that because of the fact that the samples are really collected in a distributed manner, it's not like you have a central computer collecting these samples and processing them. Every sample is a computer. So you have to do this with a very distributed mindset, because communicating in order to exchange this information is a power killer. So
now here again, I'm sorry that I'm the third in the punch bowl here, but I have to also raise a flag. I keep hearing the other night, and I want to bring it up because it's a false premise that the transmission is the killer. No, energy consumption need not be by transmission need not be the dominant form.
The platforms that I'm dealing with, which relate to Chris Piester's Smart Dust, which is what inspired this work, that is the case. And in fact, his company is built on the premise that that is the reason they do all the other smarts. Now, it depends on the platform. I'm considering the platforms where that is true. Okay, so it may not be a universal one, but this is my vision of, one of the visions of one way to make things work. Okay, so the question is, given that I have these low precision devices, if you have high precision devices, great, you can do those too. But if you have low precision devices, can I still get something useful out of them if I have enough? So that's the question I'm addressing. Okay, so it turns out that indeed, there is a notion of a distributed sampling theory that you can think about, and at a sort of very high level, you can essentially think about the number of bits in a spatio-temporal Nyquist interval can be conserved in the sense of, it doesn't matter whether you have, for example, this is supposed to illustrate the fact that you have a 2-bit A to D, which is sampling at Nyquist, versus a 1-bit A to D, which is sampling at twice Nyquist. They will both give you asymptotically the same reconstruction performance. And that performance is going to be exponential in the number of bits that you have. So obviously, as I employ a bigger and more precise things, I want the reconstruction to get arbitrarily good. And this is the best known trade-off. And in fact, you can actually have a lot of flexibility in the sort of trade-off between how precise every individual unit is and the number of units you deploy. So it's kind of a total cost type of perspective. And in fact, you can address a scaling law, if you will, on these kinds of information fields. And effectively, what happens is the distortion will be essentially inversely proportional to the spacing, or the number of 1 over n, where n is the number of nodes that you employ per Nyquist interval. And you need concepts, I won't go into the details, but you can actually do this in a distributed manner, where essentially concepts like dithering and distributed coding, which I'll talk about a little later, will come into play. So this is kind of a summary of what happens, and it turns out that even if these sensors have some errors in them, like if you have bit flips because of noise on the cameras, because of the large numbers, you can be robust to within where the scaling law doesn't change. The constants will change, but the scaling law will not change. Yeah.
Can you explain why these are the rates heuristically?
Heuristically, what is happening is that it's related to the fact that you can, the way the scheme works is actually that instead of, by having many, if you think of a 1D case, you are essentially translating the resolution you have on the x-axis to resolution you want on the y-axis. So y-axis is the amplitude axis. That's where you want good resolution. I have very poor resolution there, but I'm taking lots and lots of samples. I'm oversampling like crazy. So what happens is, it turns out you can, if you add the right kind of dither to that function. So instead of sampling the signal itself, you sample essentially signal plus dither. And you look at in the 1-bit case, the 0 crossings of the sum. So the 0 crossings capture the resolution of what you want on the amplitude axis. So in order to get the 0 crossings to finer resolution, you need more devices. So that's roughly the intuition. Yeah.
Is this related to stochastic elements kind of behavior, where you're saying that you're going to design your dither or noise kind of thing?
No. The dither is actually related to forcing sort of 0 crossings in every Nyquist interval. So it's not the same. Okay, so this is kind of I just wanted to give a glimpse of the fact that sampling type things can benefit from this numbers business. I want to now address another issue relating to storage, retrieval and storage. So this is a case where I have a large network, and some of the nodes, the yellow nodes, are producing data, and the black nodes are going to store data. Now, the important assumption here is that this data is distributed to begin with. So each of these is a datum, and data is not in one place. It's all over the place. Now, the traditional approach, so suppose I wanted to get this data at this computer here, this is my controller, is the typical approach is to pull the data by querying and saying, okay, I want sensor number 34, 85, and 77, or something equivalent to that. You need to do things like locating the nodes and routing them, and potentially that can be high latency depending on how bad the network is congested at the time, and there's potential for unreliability depending on the on the instantaneous aspect of the situation. So one motivation is, can we kind of improve the quality of service, if you will? That suppose data needs to be present or needs to be accessible fairly fast with low latency. It's important information, for example. You would like the concept of actually having the data available everywhere. So it's not a new concept. So having a ubiquitous data access so that no matter where I go, I have data available. That will obviously improve robustness, because if data is not here, I can move over here and get it from there. And it has potentially low latency. Of course, there's a price to be paid, in that the network has to be made ready to make the data available at your fingertips. So, of course, let's pose a very sort of specific problem that captures the spirit of what this means. So suppose there are n storage nodes. These are these black nodes. And let's say k is some fraction of n. Say alpha is a is something less than 1, say 10% or 30%, are data of interest. And the rest are like storage or relay nodes. And to be specific, each data node produces one packet of information. And the data nodes are, of course, spread out. And my goal is to kind of get all those k data packets of interest, these k packets here. And of course, I can always have mirror the sites like Akamai does and have a copy of everything available everywhere. But that would mean that I would need to have enormous amount of network-related storage everywhere. So I'm going to disallow that by saying that every node can store one packet and no more. Every node gets to store one packet. So question is, how do I facilitate that, and what are some things that we can say about this? One alternative is to have a centralized solution. Get all the data, pump it into a central node, let him do some processing, and then let him distribute the data out to all the black nodes. So that would, essentially that's what I'm saying here. And of course, the process of distributing that would involve doing a code, for example, an NK erasure correction code like a Reed-Solomon code, or these fountain codes that Luby and others have done. Essentially, they have the property that given any k out of these n, you have the original k information intact. MDS codes, they call it. So that can be done. And each storage node will only need to store one of the encoded packets. And of course, since by definition these are MDS codes, meaning any k of them will get can retrieve all the data. Any k storage nodes, if the querier is moving around, he can ask any k of them and he'll get the data at his fingertips. The problem with this is, as the network scales, there are two things. One is that this is not going to scale because you have to have more and more guys. This guy has to process more and more information. You can build the system up that way, but it's certainly not scalable. And also you are subject to single points of failure. That if this node is down at the time, or if it is compromised, then you have problems, security issues. So one idea is to think of it in a completely decentralized way. So here's an example. So here are these sort of data nodes, and they're going to randomly pick points in the network to store their data into. So they're going to shoot randomly into the network. So A is going to go here, and then B, and so on. And what are these guys going to do? They're just going to randomly combine these things and store them. And the combination, in the very simple example of, say, binary 2, would be doing just binary 2 addition on XORing. So this node would get A, this guy gets B and C, so he just XORs them and stores B plus C. This guy stores A plus C, and this guy stores D. So note that these four nodes, so if this guy is here and he wants to probe the four nodes closest to him, he'll just ask these guys, and as long as these four information pieces give you enough information about A, B, C, and D, he can solve for them. Like having linear equations in, as many equations on nodes. So he can solve for A, B, C, D. So the key question is, how many such random shootings do I need to do? So assuming that each one is spraying his data randomly into the network. Of course, I'm not going to talk about the fact that during there's a routing involved. It's a random thing. I'm going to abstract away any routing issues. So assuming the routing is in place, the right way is to do them jointly. That would be the next step. But for the moment, it's an interesting question to ask, how many such random shootings do I need in order to facilitate that?
Sure. What is the underlying application? You have these nodes that collect data, and then why do you have why do you want to have all the other nodes essentially
that's what he's going to talk about.
have the information?
Because one aspect to that is the fact that I would like to have very, very low and robust access to the data at all times. I could have a collector who's moving around and he doesn't want to kind of pick on one part of the network versus another. Another case which I'm looking at is actually to have the summary information, which is it's like you can build an information pyramid on this, where very important summary information should be available everywhere. Global information, headline news should be everywhere. No matter where you go, I should get it. And more local information should be more locally processed.
I think we can combine this with some cryptography kind of a thing where I have a big data divided into many packets and only a few people know how to put them together, what they want.
I think
security-wise.
Right, security-wise also it has some advantage in that no one person has all the data. So if you compromise a few of these guys, you still are not going to get all the data.
Okay, and I mean these are sensors, not persons or depositories of data. So the sensors.
This could be for ad hoc networks also. In fact, there are ad hoc networks.
Entirely different set of constraints.
Yeah, I agree. Yeah.
But I mean, for the sensor application, I just can't see what is the persuasion.
I think one important thing is that you may not, for example, it may be easier to spread the information out. Essentially, it's for low latency access. If you want time critical information, you may not want to always depend on asking these
But who wants the information? Some human being, some user. So that user is not going to go out and sample for sensors, okay? I mean, what is the setup?
No, you'll have some unmanned vehicle going by and probing things randomly, right? You can have an aerial vehicle which is collecting the information, and it can collect from any. It may be very dangerous to go inside. You may only want to circle the periphery, or as I said, you can have an information pyramid thing where extremely critical summary information you should know everywhere so that you can take action on it. So anyway, in terms of the main results, what you can show is that you need to essentially hit only a logarithmic number of nodes. So as n is the size of the network, C log n, independent random shootings per node are sufficient with high probability. Now, you can also show by a coupon collector argument that order of log n is necessary. Without order of log n, you're not going to get the job done. And therefore, you're order optimal. So this very random way of spraying information is as good as it gets.
So do you think your full connectivity, that is, really can poll all of the nearest neighbors?
No. What this guy does is he just picks. I'm abstracting away the routing.
Yes.
So you're assuming some geographic routing is in place. He picks a random place in the network, and then he says, "I'm going to send my data there." This guy picks another random. So they all are doing that, and they're going to spray. Essentially, they're going to find the logarithmic number of people in the network and spray their data into. That's the assumption.
Randomly.
Randomly.
And can be arbitrarily far from.
Can be arbitrarily far. In fact, you do need to be. It has to be uniformly picked.
Yes.
It has to be uniformly picked. So there's a price to be paid for this.
Is that realistic, really?
Well, you can make it local, right? So
Yes.
in other words, you can think of this argument as being in sectors. So anybody in this sector will contain this information. So it has to be made practical with how much. It's a trade-off between how much at the fingertips you need versus the price needed to enable that, right? It's the cost that you have to ask.
The way you set it up on the previous slide, it looks more or less exactly like the linear network coding problem.
Right, it's not quite. I was going to say that it's a little different because of the fact that these guys are independent. So I can talk offline about how they're different. Yeah.
If you increase the number of data nodes, wouldn't it be dependent on those string nodes? Because it proportionally increase the number of linear equations.
Yeah, I'm assuming that k over n is constant. N is increasing and k is also increasing. So say 30% of the nodes are always producing information. Whether n is 10 or n is 10 million. That's the setup here. So k over n is held constant.
So the fact that you can localize the algorithm kind of obviates the need to know all the nodes in the network. Because the way you described it, you said originally you can send to anywhere in the network, assuming that I presume that you know who participates in the network.
Right. I mean, you can. This is just meant to show that if you want this network to have the data, have this feature.
But implicit you assume that you can send to anyone in the
network. Implicitly, I'm assuming I can send to anyone.
In response to Bard's point, what you said is that by localizing, I'm still ahead of the game. I'm still having a login order. Is that the argument?
Yes.
So you don't need to know who's in the network.
I don't need to know who's in the network.
Because otherwise, that would certainly not be practical in a sense of network.
I'm just exactly. So I'm okay. So looking at the time. So again, you can how the high probability business is related to the work, the network coding stuff, which I will talk a little more about. So essentially, it has to do how likely is it that this is going to happen. Has to do with the fact that I need to generate k-independent equations. Now, it has to be done in a field whose size is big enough, and this is the guarantees that you can make in terms of how likely you're likely to have this feature enabled. So essentially, depending on the size of the field, you will be exponential in the size in terms of the probability happening. And this is not the same as fountain codes in a couple of regards. One is that the data starts out being distributed. That is the key starting point that is different from almost everything else. In all the other things that I know of, data is in one place, and then coding happens. Here the data starts out being spread out. And there are some other differences which I can elaborate. And I think the most interesting aspect of this from a information pyramid standpoint is the fact that you can think of multi-resolution aspects to this information storage aspect where, again, headline news is made ubiquitous everywhere at the right cost, so K will not be that big for that. And more important information you can keep more locally. So you can build an entire information pyramid that will probably be of value. And I won't go into the proof ideas. I don't have time. Okay, I want to talk a little bit about something even much more futuristic. I'm sure you're going to chew me out for this, but I'll do it anyway. So the motivation for this comes from the fact that I'm actually interacting with a circuits person who's also very wide thinking. So motivation is the drive for low power, cheaper, and smaller. Okay, so this is my colleague Jan Rabai at the Berkeley Wireless Research Center. So these are numbers I got from him. So I'm just a messenger here, so I don't know anything more than this slide. So if you have any questions, I'll refer them to him and then I'll get back to you. So on the market, you have 10 milliwatt type of devices. Prototypes apparently can be made for 3 to 4 milliwatts. And of course, there's a lot of interest in some of these projects on doing energy scavenging through vibrational and solar and other energies. And apparently, you can get something of the order of 100 microwatts per square centimeter. So that's another reason why you want very high spatial density. So you can sort of harness a lot of this energy. So the cost is about $50 each for these kinds of devices. Prototypes sell for about $5, but the goal is to get them to much cheaper. Again, sort of the economy of scale will kick in, but we'd like to get this under $1, 10 cents, even a penny if you can. And of course, the vision is these have to be small enough to be mixed with paint. Okay, remember that the smart walls thing. So that's kind of the vision that. Yeah.
These are pure radios. Do they have any HD conversion on board?
Yeah, they will have. I mean, there are issues. So let me tell you some of the driving applications or philosophy behind this. So one problem is that digital subsystems have been writing Moore's law, and they still tend to do that. But again, based on my information from my circuits colleagues, radios have not been that successful in scaling, mainly because analog components don't scale very well. And what he tells me is the off-chip crystal needed to do very precise clocks is one of the culprits, as you can see here. So the question is, so what he's interested in doing is to integrate all these functionalities. So the fully integrated radio to sort of see whether power, cost, and size can all be attacked on one footing. So in this context, this is kind of the interesting picture that I learned talking to these guys, is that, well, assuming you want to do narrowband communication, so the radio frequency is something here. If you use a very precise crystal oscillator, which is expensive, you will nail it down. The center frequency is exact. But if you use sort of cheap devices, like on-chip LC resonators or MEMS type of devices, they are much less precise, but much less expensive as well. So the cost factor comes in. And the interesting thing that I heard was that if you wanted to target a bandwidth that's narrowband like this, the manufacturing process variations in hitting that, the spread in the process is many times, an order of magnitude more than the very signal bandwidth you're interested in. So it's a huge problem in that it's you can either try to be precise here or to live with this variation. So our philosophy, as you would have guessed, is to live with the variation. In fact, to embrace it. So the point has to do with, can you admit? So let's say that you have narrowband radios, and let's say that they are picked out of a manufacturing process, and the transmitter and receiver frequencies are arbitrary, and they are whatever they are born with, whatever nature has endowed on them. And the goal is to see whether we can still instrument reliable communication with a swarm of these things. So the idea here would be that, of course, if I pick channel 55 to transmit on, maybe nobody is receiving on channel 55, and then that wouldn't be good. But let's see how the numbers stack up. So that's the question we're interested in. Can a reliable communication network be made out of such very unreliable elements, where I don't even know where I'm sending? I know I'm some random channel, and some other person is listening randomly. So, and the answer is yes, if you have enough of them. Okay, at least in these abstract models. So this is just the starting. This is very, very preliminary work, but I just wanted to share with you that there's something interesting in this. And the idea would be to do very random communications. And so you have a source here. So let's do a point-to-point case. Source sitting here and the destination sitting here. And these are supposed to be multiple hops that go through between source and destination. So each of these is a section or a block where I have lots of sensors here, lots of devices. And the goal is to hop from left to right in this fashion. So we're going to do multi-hop communication from here to here. So transmitters in block B choose a random channel independently. Receivers in channel B plus 1, in block B plus 1, again listen in on a random channel. And then that's how the whole paradigm evolves. So here's kind of a caricature of what's going on. It's like balls and bins. So transmitters are sending on a random channel, and receivers are listening to a random channel. So if there are n channels here, so this might be a typical instance where 3 people pick channel 5, 1 picked 4, and so on. And of course, so nobody is on 2, nobody is sent here, and exactly 1 person sent here. And we'll assume a very simple model where if 2 people are talking on the same channel, they're going to collide, and I won't get anything good. And if nobody is receiving on a particular channel, even if somebody is sending back, that's lost. But the good situation is when 1 channel is picked to send, and at least 1 listener is listening to it. That means that packet survives, or that data survives, and it's sent along. Okay, so that's the assumption. So now you can do a very simple argument, a sort of probability argument, to see that if I commit to n channels, and I tell you that you have n transmitters and they have to choose from the same sort of probability mass function, and they have to choose the optimal thing for them to do in order to achieve the success of having only success, to maximize the chance of success, is for you to have n transmitters and they choose the channels uniformly. In which case, the probability of success is 1 over e.
Okay, so there is work that's been done with the time domain instead of the frequency domain, which is exactly to find out who your neighbors are.
Right.
And there's a lot of algorithms which are not exactly to this.
I'm sure it's very, very connected to in fact, the Aloha algorithm and other things also.
No, I don't mean that. I mean algorithms by which you have policies of deciding in which random slots you will transmit, how many slots consecutively, and so on, and which slot you will be listening to, so that randomly employed nodes find out who's their neighbor.
Right. In this,
so that's exactly this problem.
Yeah.
And
I would love to know more details of. That's very useful information. So in what we are going to do here, we're going to increase the end-to-end throughput. We're going to have multiple receivers per node. So again, this is something we want. This is based on, again, information from my circuits colleagues, that if you wanted to sort of increase your diversity, you want to receive on more channels. Let's say L is some small number, but not 1. 1 is a bad number, meaning transmit on 1 but receive on several. That's still, as long as they're imprecise, the trade-offs supposedly are still in the favor of favoring this, as long as L doesn't get astronomically large. The benefit is that the nodes will get to hear more than one transmitter, and so intuitively you believe that the packet has a larger chance of survival, because more guys are picking you up. Of course, you can forward one of the packets, or you can combine them using network coding. So let me give you an overview of network coding. So the goal of this is a very interesting and hot area in coding theory right now, which was pioneered in 2000 by Al Schwede, Raymond Young, and collaborators. And the goal here is you want to send A and B to both R1 and R2. So it's a multicast problem. So you want to send these sources A and B to both R1 and R2. And of course, there's a max flow min cut bound, which says that I cannot do better than the min cut to the worst guy. So for example, if you take R1, at most you can get, suppose these are unit bandwidth links, you cannot get more than 2 units for 2 packets per unit time. But of course, this is not possible to do with your classical forward and route type of mechanism. For example, A and B come here, and this node has a decision to make whether to keep A or B on the way forward. And whichever one it keeps, one of these guys is not going to be happy. So you cannot send A and B to both R1 and R2 if you just forward one of these two alone. Instead, if you mix them, which is what network coding is, you get A plus B, and then you're in good shape because both of them have enough information to retrieve both A and B. So this is the overview of network coding. And based on this, this essentially says that the original work essentially says there exists a linear network code that can take care of, that will get you the max flow min cut bound. And the achievability of the max flow has been studied in great depth by many people in recent years. Ralph Cotter and Muriel Medard and company have championed this cause. And essentially, you can also do randomized, instead of being very precise, you can do randomized combining of these nodes, of these elements in the GFQ. Again, very similar to the result I showed you earlier. As long as Q is large enough and it grows, almost surely things are going to work. And of course, most of the work that I'm familiar with in this area has focused on having a network, having a topology, and then finding out what is the maximum throughput that you can get out of that.
There is more work here, just completed, to be presented in April in a network coding workshop, which looks at the wireless network and extends this, because you have to be careful with the wireless case.
Okay.
The cut capacity could not be the sum of the link capacities.
This is the one in Italy that's coming up. Okay. Yeah, so...
But it's been done here, we can tell you.
Yeah, I'd love to chat with you.
This random network coding here, what is the ensemble over which you average? Is that a fixed network and then you randomize overall encoding? So what is the random?
Oh, you mean their work?
The last line on the slide, random and CHE is random with respect to what?
Oh, random with respect to picking coefficients in GFQ.
So it's the network is fixed.
The network is fixed, given to you, and then if you randomly combine things out of a GF feed, you just, and then that will give you, with high probability, as Q grows. And of course,
one systematic choices too, taking advantage of the topology of the network.
Right. So in some sense, the work that I'm familiar with, again, not including new stuff that has been going on, mostly has been focused on topologies that are known and finding out what's the throughput and how you do things. So I'm actually interested in the opposite problem. I don't even know the network. It's a random graph for me. So I want to even find out what is the maximum flow, because I just committed to doing a bunch of random events, and I don't know what the flow out of that network is. So that's really the problem of interest to me. Of course, network coding will be a commodity that I need, that I will use once I know what the flow is. So that's more my style in this work. So here I'm going to represent this as a random graph. You have n nodes per block. L is the input degree to the input node of each stage, and H is the number of blocks, number of stages of the hop. So H is the packet hopping along from left to right. N is the number of nodes in every stage. So the random graph representation would have something like this. These are the hops that are going through. And every vertex here connects to L previous guys in the previous column, which are the L untuned radios. These are the receivers. You're receiving in on L channels here. And then because of collisions, the death process, the 1/E thing that I told you about, these guys are knocking each other out. And then I want to know, what is the max flow out of this network? So if I put a big node here and sucked it out here, how many sort of disjoint paths can that take? And because if I wanted to do just routing, there will be a route, but I don't know what the route is because I'm doing things randomly.
We have a solution to your problem. Yalin here, Yalin's up to you here. We have a solution.
Okay, good.
This is the problem exactly.
Okay, so the vertices are deleted with this probability and collisions have this probability. And I won't go through the details of the results of the proof, but essentially you can show that for any constant L greater than E, because P is 1 minus 1 over E here, so E is 2.7, so L greater than 3, L 3 or more, you can get throughput that is linear in N. In other words, if I didn't do routing, I will essentially, with very high probability, get only one packet through. One guy will dominate and kill all the others. But if I did network coding, if I mix them up, I will get a throughput which is linear in N. And the interesting thing is that the constant that you get is very close to N over E, with high probability. In other words, all the loss happens in the first stage, and then the rank gets preserved. Even if I go an exponential, sub-exponential number of blocks. So H doesn't need to be very small. It can be even linear in N. As long as it's not exponential in N, I will get this throughput guarantee. Of course, these results are based on bounding techniques, so the actual throughput turns out to be much better in simulations than the guaranteed throughput, because they're based on bounds. And when we did these simulations, even for small values of L, we pretty much get very close to the 1 over E. So that's of practical interest if you want to build systems on. So in fact, we are trying to build this with Jan Rabai in the VWRC. See whether, in fact, we can actually make a system out of this. Okay, so finally, I want to talk a little bit about video sensors, because that's really the topic that's near and dear to me. I'm a video guy. I'm just been scrambling along in other areas just because I've been interested in them. But I do want to talk about a project which I think is an interesting one, which came about from my work on sensor networks. Of course, video cameras are very much sensor networks, video camera networks, if you will. So again, if you look at emerging video applications, you have lots of digital video cameras and surveillance networks and teleconferencing and home networking. So wireless video is rampant. It's one of the biggest growth areas for multimedia in the projected future.
So low power or low energy video sensors in the middle. In the third bullet, you said ultra low power video sensors. You really need power or you need energy? Or both?
Depending on the deployment. Some of them are power. They are, but I don't mean it in a very specific way. I just meant it in a general way. I don't need to. So these kinds of devices are kind of demanding certain architectural requirements which are somewhat different, a little bit more involved than the usual ways that sort of video broadcast originated, which has driven sort of video codec sort of architectures like MPEG, which I talked about. So you have high compression efficiency you need. The important thing is that the footprint in the wireless units may be small and they may have battery type issues. So you want to try to lower the complexity at the ends. At the same time, losses have increased a lot because you're on a wireless channel. And for certain applications, latency is very important. Interactive applications, streaming applications, and so on. Now, how are current standards dealing with these issues? What do the standards committees do? So I have some views through my interactions with Qualcomm. Now, current video standards, there are two workhorses. The most popular one is MPEG, of course, all the MPEG family, which are essentially based on motion compensated predictive coding. The idea is very simple. it's almost trivial. If you have a current frame, so most of the redundancy in video is in the temporal dimension. So you have to exploit that and remove that. And the way they do that is very much in a brute force type manner. So you chop up the current video frame into blocks, and for each block you look for a match in the previous frame. Which block in the previous frame best matches you in whatever sense, usually squared error or absolute error sense, sum of absolute errors. And the difference is, so you send the indicator to where is the best match evolved, which is the motion vector, the motion field, and then you also send the prediction error, and how wrong you were in doing the prediction. And at a high level, what are the features? Well, there is high compression efficiency because you are removing the temporal redundancy, and more sophisticated sort of motion compensation techniques will do that better, but that essentially means just try many combinations and pick the best of all. So that's been roughly the way the standards have evolved. And of course, one thing that you note here very clearly is that by definition, the architecture is geared towards making the encoding heavy and the decoding light, because the motion search is the bulk of the complexity, depending on what platform you're on, but nonetheless it's sort of indisputable that the motion search is the killer. Now, it's also clearly, because this was not geared, this is a source coding problem, this was not meant for transmission over a channel. So if you wanted to worry about a channel, you can do a channel code on top of it, but then that has some latency issues. So, in other words, the point is that the more sophisticated you get here, obviously the more fragile you're going to be to channel losses, as all good source code should. Now, image coding, still image coding philosophy, which is motion JPEG, has low complexity, is robust to transmission losses, and that, the main reason you have fragility here is because of the predictive coding framework, where you have an anchor frame and dependent frames, like DPCM. So once you lost one of the anchor units, everything that depends on it is lost until help arrives. So this is called the drift problem, until you reset the system through an intra-frame or something like that. Okay, now image coding, motion JPEG approaches the problem by saying, I don't care about temporal redundancy. I'm going to treat every frame as an independent unit. So you get what you pay for. So you get very poor compression efficiency, almost an order of magnitude worse. But obviously it's low in complexity, there's no motion search involved, and it's obviously robust, because if I lost frame 40, just wait for frame 41. There's no dependency. Okay, but this is at odds with the evolving architectures or the evolving applications, where it doesn't make sense to put a heavy encoder here, because this guy is potentially not the heavy guy. In fact, you want this to be light. So what you would like is to, for example, have the decoder pick up the slack for the encoder, in which case you can have a network device, because networks are fine to have complexity inside. You can have a big processor here. Move the complexity into the network. Can you do that? And can you do that efficiently? So that's kind of what inspired the architecture. Again, follow the complexity story. Where there's cycles, do that. That's kind of the common thread. So this stands for some acronym, as you have to have in Berkeley to survive. So it's called PRISM. Oops, I think I had two of the same. Sorry.
I don't want to belabor this point, but there is so much confusion out there, mixing things that we learn to distinguish in high school between power and energy. So power efficient or energy efficient? You say the prism is not power. You really mean power efficient or energy efficient? It's very different things, as we know. But which one of the two do you mean?
I mean power. But I'm not sure I'm qualified to answer that. Maybe I can answer it to you offline.
Power is like the quantity of energy per time, right?
Exactly.
Yeah.
So it's more or less related. If
They're
one is
related,
low,
but they're
then
very
the other
different.
one
If you are energy efficient, you want the integral to be low. If you are power efficient,
That's
you
not
want
the only definition of efficiency, right?
small.
Right. So let's be clear. What
Then they define it efficient.
is it power or energy? And
And what efficiency mean, I tell you what I mean, right?
Is it illegal or is it maximum? I define it.
I mean, it is very fundamental, it's very important, it can spread confusion to an incredible degree that one would not anticipate.
Not to
It's
the
very
real,
different things.
not to the real design.
Okay, so based on the time, I guess I'll abbreviate this part. But I just wanted to give the highlight that the architecture for this new video framework that I was talking about actually comes from the notion of distributed source coding or distributed compression, also called source coding with site information. And the idea came about when we were playing with removing redundancy, spatial redundancy in dense sensor networks, where if you're sampling a temperature field, obviously there's a lot of correlation in the nodes that are sensing this. So when you want to send this information over to some interested party, you don't want to kind of send independent data. Well, collaborating is also expensive, so can you do this in a distributed way? So the encoder needs to compress out the sort of poster child for this problem, if you will, is where the encoder has X, decoder has Y. So let's say Y was already shipped as an independent variable, and now X is being sent. So obviously the best you can do is to send the uncertainty in X given Y, the entropy of X given Y. That's the fundamental limit, which is how much information remains in X. And information theory teaches us from 30 years ago, Lippian and Wolf theorem, that in fact, indeed, X can be theoretically compressed at the same efficiency as if Y was present at both ends, which is a very, very intriguing and interesting thing on which other people, Prakash and others, have also made a lot of interesting advances on. There's a similar kind of result in the case of, this is for lossless compression with discrete outputs in combined view. In this case, you have a lossy case because, in general, video is not necessary to do it losslessly. It's a lot of redundancy, right? So you want to do lossy versions. And that was done by Weiner and Ziv in 1976, 3 years after Lippian and Wolf. And again, in the case of, I won't give you the entire Weiner-Ziv formulation, but I just highlight to you that in the case when X and Y are jointly Gaussian, again, the rate distortion performance with the mean squared error metric for reconstructing X with X hat is as efficient as if Y was present at both ends. So in the video formulation, because I'm running short on time, I don't know how much. Should I be quitting now or a few more minutes? Almost 5 minutes. 5 minutes. We did. Yeah, I can put it. So the point here is that so essentially there is a way of cleverly exploiting the site information. That's the bottom line. And to think visually or intuitively, you can think of Y as being a noisy version of X that has been received over a virtual channel. And you want to leverage the fact that this is a second transmission. You already had one transmission. Okay, so at a high level, that's what's happening. I'll give you a geometric interpretation of this. In the Gaussian case, of course, everything is a sphere in the Gaussian case. So what you do is you actually, if you want to send a source, which in a high dimension will lie on a hypersphere, I'm going to, a standard rate distortion problem would be one of putting a lot of quantization cells on the space. Think of this as a VQ, a vector quantizer. And each of these balls contains the resolution with respect to which I want to resolve my information, right? So this is the radius of these balls, tells you how much distortion I'm going to incur. So the smaller these radii are, the better my distortion, but then the more of these balls, so if I were to do this in a classical standard way, I would need to spend log to base 2 of the number of balls. Right? I need to identify this ball and not any of the others. Now, the key intuition behind the Weiner-Ziv formulation, or the Lippian-Wolf, is you're going to randomly color, or constructively color in some way. You're not going to use as many colors as there are balls covering this big ball. Okay? So you're only going to use a few colors. And then you're going to signal only which color your source code word lies closest to. In other words, in this case, it's closest to this orange ball. So I'm just going to say that it's the orange ball is what happened. Of course, there's lots of orange balls, so the decoder doesn't know which orange ball the encoder had in mind. But that's why it needs to use the site information. That is why. It already has something that is related to X. And that is the Y. And what Y will do is, as long as Y is sufficiently close to the radius of this separation between the two closest balls, small balls, I will decode this like a standard channel coding problem. It's like I had a noisy version, I decoded to the center of that sphere, and then I got my guy. So that's the intuition. And the interesting thing is this works as well as if I had y at both ends when things are Gaussian. So pretty remarkable result. Okay, what we're going to do for video is essentially a slight modification of this idea. The modification comes about, there's a little twist here, because remember in the video case, what's happening is that I'm searching this previous frame for this. Think of this as the unit that I want to encode. I'm searching for this in some space here, and there's a whole bunch of those candidates. And I'm going to pick one of them. I'm going to pick those as y1 through ym. And then nature picks one of these randomly to say that I'm going to correlate with x. And the correlation noise is the prediction error. And that's the video generation process, if you will. Okay? X is produced by randomly picking one of these guys and adding some innovations to it. And these are the candidate predictors. Classical MPEG, what it does is it goes and searches to see which of these nature picked, sends it in a motion index, spending this many bits. These are the motion vector bits. Log of m divided by n is the number of pixels or the block length. And plus it sends r bits per sample, if you will, for the sending the difference. So r plus 1 over n log m. And then you reverse the process at the other end. Of course, now, if I want to have a chance at this working, where I don't want to do work at the encoder, I should avoid doing motion search. Can I do that? In other words, even though y1 through ym is here, I'm going to put a blindfold on and say I don't have it. And then I'm going to be given the same rate as the other guy. And the question is, can I match the performance of this without doing any search here? And the answer is, again, as you would expect, it can only work in the Gaussian case exactly. In the Gaussian case, the answer is yes. I don't need to do motion search at the encoder. Meaning, what is Gaussian? The prediction error is Gaussian. So the innovations process, if it's Gaussian, then I can do just as well by not doing any work at the encoder. And what the implications of this are, that the high complexity of motion search is no longer at the encoder, because this is simply one of assigning a color to the code word, which is a very simple operation, if you will. And the complex operation has been moved to the decoder. And I won't go into the details of this, but essentially what you have is a parallel bank of these decoders, each one conditioned on one of the yi's, the candidates, as the possible guy. And when you do it right, only one guy